title of this notes is Differentiability. And the outcome, so you're going to be able to answer the question, what are the implications of differentiability? It means, so what? Why do we care about a function being differentiable? So first of all, it's important to talk about when the derivative might not exist. When the derivative might not exist. And so we have a couple scenarios. The first scenario of when a derivative might not exist is at a corner. Like your absolute value function. When you get a corner on your graph, at the corner, that corner point does not have a derivative. Because if you think back to the section 3.1 notes, you have a left-hand derivative and a right-hand derivative. Remembering that derivative is slope. Coming in from the left, this has a negative slope. But coming in from the right, it has a positive slope. And they're not the same. The left hand and the right hand aren't the same. So there is no derivative at that value. Another place where you might not have a derivative is at what's called a cusp. A cusp is kind of like a corner, but instead of going straight into the corner, the graph kind of rolls into the corner, like a bird. So this graph would be like this side is the square root of x, and then we have over here the reflection of that. I'm not sure that equation. But if you have a cusp where you kind of roll into a corner, you also have a place where you are not differentiable. A third scenario is what's called a vertical tangent. So when the tangent line goes straight up and down, you don't have a derivative. I'm going to move those. So an example is your cube root function. If you think about your tangent lines, here we have a positive value increasing, and then right here, our tangent line goes straight up and down. It's a vertical tangent. What's that slope? It's undefined. What does that mean for the derivative? It is also undefined, so it does not exist when you have a vertical tangent. The last example is a discontinuity. Any type of discontinuity means that you don't have a derivative. So the most common type of discontinuity we're going to see is a hole. At that hole, there is no derivative. Okay, so how can you tell that the derivative does not exist? So you want to think of the graph. Think graphically. All of these are what I call interesting points. A corner, a cusp, a vertical tangent, or a discontinuity. Something interesting is happening there. So you want to think of the graph of the function. Think about where on the domain does something interesting, like these four things, happen. And then at those points, you're going to want to check for a derivative. You're going to check both the left and the right-hand derivatives. And if they match, you're differentiable. If they don't match, then the function is not differentiable at that point. So the next idea is that differentiability implies local linearity. So if you think back to your essential question, what are the implications? One of the implications of a derivative is that the graph is locally linear there. What do I mean? So local means close by. Linearity means that it's a straight line. Local linearity means that if you zoom way close in, local linearity means zoom way in. If you zoom way in, your graph will eventually look like a line. It won't be a perfectly straight line, but it'll look like a line. That's supposed to say like a line. Okay, unlike my writing. Your graph is going to look like a line. So even your sine function, if I zoom way in to this piece right here, and I keep zooming in, so zoomed in, I'm going to do the zoom in red. Zoomed in, that's going to look like this. That's this piece in the green. I've now redrawn it over here in red. And if I zoom way in again, you can see as I keep zooming in, it's getting closer and closer and closer to looking just like a straight line with negative slope. If your graph is differentiable, that means that you can zoom in far enough that it'll eventually look like a line. Now, we've been calculating derivatives by hand. Remember that limit as h approaches 0 of f of x plus h minus f of x all over h, that equation that you love? Whole time, you could have done it on your calculator. There is a way to calculate numerical derivatives on the calculator. So what I'm going to show you is I'm actually going to switch my screen to a calculator screen. So if you turn your calculator on and you go to the Math menu under the Alpha button, and you scroll down, there's an option for N-deriv. The N stands for numerical derivative. If you look back, that's our title, numerical derivative. If you hit this button, if you have the update, you'll see this screen. If you don't see this screen on your calculator, come let me know and I will show you the commands. In the first space, you're going to put X using your variable key right here. Remember, one of our notations was dx. In the next blank, you're going to put your function. So let's say your function is 2x squared plus 13x. Okay, so that's the function. And then over here, after the line, x equals, you want to know the derivative at what number? I want to know the derivative at 8. Press enter, and the calculator's done the calculation for me. So the derivative at 8 of this function, 2x squared plus 13x, is 45. I want to move on. What is another implication of differentiability? Differentiability implies continuity. This is a theorem that you need to know. If f has a derivative at x equals a, then f has to be continuous at that point. If your derivative exists, then you must be continuous. If your derivative exists, then you must be continuous. The converse of this statement is also true. The converse means that we're going to put the theorem in reverse order. So if f is continuous, if you're continuous, then you must be differentiable. And we're going to abbreviate that diffable. As long as you're continuous, you're diffable. So if you think back to the very beginning of these notes where I said, how do you find a place where you're not differentiable? I'm going to go back to the first section. Where do you fail to exist? Those interesting points that I'm talking about, those are points where I may not be continuous. If you're not continuous, like in your discontinuity, you definitely are not differentiable. Now you might be noticing on this screen there's some other examples where we're not differentiable and we are continuous. So we cannot say hold on one second, I think I'm saying the converse backwards. Okay, I'm proving myself exactly right here. So the converse, I am saying the converse correctly, I'm sorry. If f is continuous at x equals a, then f is differentiable at a. What I'm showing you here are counterexamples. So this converse is not true. And we have these counterexamples. Now, let me back up here. If you are discontinuous, you're definitely not differentiable. But it is possible to be continuous. It is possible to be continuous and not differentiable. And these are 3 counterexamples. What is true is what's called the contrapositive. Don't get so caught up in the language here. But if you flip the statement and put nots in it. So if f is not continuous at x equals a, then f is not differentiable. This is a true statement. Converse is not true. The contrapositive, that's what this red one is called. That one is true. Okay, so let me recap here. If you have a derivative, you must be continuous. If you are continuous, you may be differentiable, maybe you're not. We can't always say. See the beginning of your notes for examples. If you are not continuous, then you are definitely not differentiable. The last idea here is the intermediate value theorem. It exists for derivatives. So as long as f is differentiable on a domain, f is differentiable on some domain from A to B, and you have some value, the derivative at A and the derivative at B. Then f prime takes on every value between f prime of A and f prime of B. So let me give you an example that you might recognize. Suppose I have some function f, and I tell you that the derivative at 0 is 2, and the derivative at 1 is 5. Is the derivative ever pi? Is the derivative ever pi? Why, yes it is. Because pi is between 2 and 5. So it's between the derivatives. So that means that there exists a value, and I'm just going to call it c. And c in this case happens to be between these two x values, 0 and 1. So there exists a value c between 0 and 1 such that the derivative of f at c is equal to pi by the intermediate value theorem for derivatives. That is the end of our notes. You can go ahead and put your line at the bottom for the summary.